see how the historic data is defined. So if you go over to calibration, you go look under functions, you'll find there's something called infectious historic. Okay, this is a function, but it's a special type of function. It's a type of function that doesn't require you actually to write any code per se. It's what's called a table function. Okay, and some of you are perhaps familiar with table functions from BenSim or from other system dynamics packages. These are functions you can define graphically that dictate for a given element of the domain, what's the corresponding value in the range. In other words, for a given x value, what's a given y value. Now in this case, it happens to be over time, and what we have here is a specification of the value, particular times, the value of the x coordinate, what's the value in the y coordinate. Now, it provides some extra little pieces of functionality. One thing is, it allows you to specify how to interpolate between data points. So suppose you only provide, a modest number of data points, and yet in the historic data, and yet the model is simulating at a very fine-grained resolution, and we want to compare the two. We want to say, sort of, what did the model predict versus what did the historic data predict. We might want to interpolate between those historic data points and say, roughly speaking, the historic data would have reported this. And we can specify the interpolation algorithm there. So I don't happen to remember off the top of my head all the different algorithms, but linear is sort of the most obvious one. Then there's a spline one, which has additional sophistication in the sense that it involves curvilinear sort of interpolation, and there are certain fixed boundary conditions over which it varies. It has to have a certain slope, I think, at the connecting points. So the 2 points have to have the same slope when they catch up, but basically it would allow for more wiggle between some of these things. So suppose you only had points here, here, and here, it would allow for sort of a smooth interpolation in terms of some of the derivatives. And then I don't know what approximation is, we'd have to look that up for what the option is there. But the point is, you can specify data points, they don't have to be regularly spaced, and you can specify a way to interpolate between them that can then be used when assessing goodness of fit. Yes?
Is that something I could import?
That you could import to use for your own?
Yeah, like let's suppose I had Excel.
Oh, I see. Yeah, yeah.
I mean, it's a data set, so I guess
Yeah.
I could, but it's just...
Yes, so what you can do, you'll notice here that you can paste from the clipboard. So if you had Excel, you could, some data in Excel, you just copy, paste, boom. Yeah, yeah. So that allows you to sort of populate this and not have to retype it. You'll notice there's a further option here on dealing with out-of-range values, okay? So the question here is, on the one hand, I want to distinguish sort of interpolation, where it's filling in between points, as it were, from extrapolation outside of that range. So if you know the values within this range, we'll try to fill in between according to interpolation. But if you ask for something that's earlier than the first value or later than the last one, how is it going to sort of identify what the value is? And again, you see that it has several options. It could use the nearest value. It could extrapolate in some sort of way. It could repeat, I believe, repeat sort of the sequence in a sort of just replicated fashion. I'd have to double check on that. There's some sort of custom one, but this allows you to have some measure of flexibility in the values. On the other hand, you may want to signal an error. If you know it should never be sampling outside of this, you may want it to signal you that, hey, it's doing something illegal. And within the next, the remaining lectures of the course, we're going to be spending some time talking about this is when you build up a model, how do you do so in a way that's more likely to be correct, less likely to have oversights, less likely to have problems in it? How do you not only build the right model, but how do you build the model right? And one of the keys to that is if there's a problem in the model, you want to know it as soon as possible. You want, if there's a problem, this is a good principle in your life as well. If there's a problem, you want to be alerted to it quickly so you can deal with it as quickly as possible. You don't want to just paper it over. And here, signaling error is a good practice if you're quite sure that by the logic of your program it should always fall within this range. Then if it doesn't, you want to be alerted to it as soon as possible. It sounds weird, you know, from some perspective, you want it to signal an error, but the point is, you know that there must be a hidden error if it's accessing it outside of that, and you want it to translate into a visible failure that you can then go fix as soon as possible. So, so in this case, it has an out of range error, reflecting the fact that by the logic of the model, we should never get anything outside the range. Okay, so table functions are really useful. They prevent you from having to write a lot of code to import data, to interpolate the data, etc. And they're a good sort of function. You'll notice that they're available here over in the palette just as a different sort of a function, and they can be called like any other function. So you can call them and get a value for a given point. Okay. Okay. So that's the historic data. Now you'll notice that earlier when we had this difference, we were comparing a data set infectious